All right, cool.
Okay. So last week, one of the main things we went over was how to visualize the qubits. I'm gonna just go back to the last one.
Wait, hold on. Let me stop sharing from here and you start sharing.
Okay. Where's the last week's stuff?
So okay, the helper notebook should be where most of it is included. How to visualize people.
Okay.
Yeah.
Nice. Okay. So yeah, so last week we saw how to create a quantum circuit on Qiskit, as well as put some gates on it. And let's just quickly review over that. Okay, so how we create a quantum circuit, first of all, is this is like standard imports if you launch from the quantum lab. Do all you guys know how to get there? Yes, okay. So these are the imports that come. So just every time you want to execute a shell or a cell, you press Shift Enter. So we start by saying QC equals quantum circuit, and we'll just define it as having 3 qubits for now. Okay. And if we want to apply an X gate on our qubits, remember they're like in an array form. So the index will start from 0, and the last index will be 2 if we have 3 qubits, for example. And if we want to see our circuit, we can do qc.draw, and this will show us our circuit and what we have so far. Okay. And if we want to visualize the state that the qubit is in as something called the state vector, which is an arrow in 3 dimensions, we can get these 2 things. Okay, so okay, so okay, so we're gonna have to import this quantum info stuff, qiskit.quantuminfo, and then we import state vector, which is our literal arrow. It's another name for a state. Okay. And then we execute this function called plot block multivector. We say state vector dot from instruction qc dot data. This is like long, and I understand that you guys probably will want to like paste this as in like useful instructions and just comment this so that you guys can keep it somewhere useful. And as you can see, it gives us a visual representation of what our state looks like. Yeah. So all of our states are starting in 0, and we applied an X gate to the 0th qubit, which is why it flips across the x-axis. Now it's pointing at 1 because our qubit is in the 1 state.
Yeah, and also one other quick note about this is we'll break down what this whole command means to you later on bit by bit. But for now, you can use this to take what you do to a quantum circuit and plot it as a set of block spheres.
Yeah. So with this, you might be like, oh, why is this useful at all? So one of the things we can do is let's say we don't just do 1 gate, right? Let's see what happens if we have an H gate on the 1 qubit, or yeah, the 1 qubit. Okay. So now we get this state. These are separate qubits. Okay, so far they are not interacting with each other in any way. Our qubit 0, I'm sorry for the title being dark, but it's still in the 1 state. This one, we applied a Hadamard rotation on it, okay? And it is now, this is called the plus state, if it's pointed that way, in the positive X direction, okay? That's what happens if you do a Hadamard on the zero state. And what we looked at mathematically was what happens when we do a Hadamard on the one state. Or sorry, yeah, Hadamard on the one state. So let's do it on qubit 2. And sorry, we have to first put the second qubit in the one state. So this is the same. Basically what we did was we first flipped this, okay? It was in the one state, and then we applied a Hadamard gate. As you can see, it rotated it like this, okay? This is not equivalent to a rotation around the y-axis. It is not the same, although for now, right, it was like, oh, it's a, I guess, counterclockwise rotation around the y-axis. That is not what it does. If you have a state in the middle, it'll do something completely different, okay? There are specific rotation gates that do just raw rotations. That is not what the Hadamard gate does, okay? Because as you can see, if we apply, so we applied a Hadamard to a zero state. If we do that again, and if this is confusing for you guys, just let me know. I can comment these out as well.
Don't be afraid to speak up at all if anything confuses.
Yeah. So now we start in the zero state, we apply a Hadamard, okay? Then we apply another Hadamard. And what we saw last week was that it brings us back, right? So it went like this, and then we did another Hadamard and brought us back. This is why it's not just a pure rotation, right? If you want to see visually what rotation it does, there's like a visualization on online. But yeah, it turns the plus state back to 0 and turns the minus state back to 1, okay? So this is why when we apply a Hadamard to a 1 state or a 0 state, we have a 50-50 chance of measuring 0 or 1, but that's because they're on these two opposite sides of the sphere, okay? Does everyone understand how this relates, like in 3 dimensions? Okay, and then one of the last things we looked at was what a Z gate does, okay? And if we comment everything out, let's go back to just, let's go back to just having the Hadamard gates on the qubit 1. So we wanted to figure out how to get this arrow over here, okay? And we came up with a sequence, right? Hadamard to bring it back to the 0 state, a knot, which will flip it to 1, and then do a Hadamard, which will put it over there, okay? And if we do that, so this would be QC dot H, then QC dot X, then QC dot H, okay? We realized that it does indeed flip that. Does that process make sense to everyone? And this is an important identity to remember, okay? Just keep in mind, this initial Hadamard is what's called our initialization. This is just to initialize the qubit to be in the plus state, okay? But this following 3 lines, this is the identity, okay? This is it's equivalent to the Z gate, okay? And why is it called the Z gate? Well, we had our pointer or vector pointing this way, the plus state, and now we have to rotate it over here, okay? If you look at the rotation, it is rotating about the Z-axis, which is why it's called the Z gate. So 180 degrees about the Z-axis, which is what we're going to call the Z gate, and it puts you over there. Did everyone get that? So that is an important identity, and the reverse is also true actually, okay? So if you have, let's say you're in the plus state, right? Yeah, if you're in the, if you're in the 0 state, and you want to get to the 1 state without using any X operation, you can do an H, then a Z to bring you here, then an H. It's the long way, but that's another identity. So HXH is equal to Z, and HZH is equal to X. That's just a nice identity to remember.
Yes, that's a very nice identity to remember, actually, and it's going to come useful when you learn about multi-qubit states in a minute.
Is there anything you want to add?
Um,
Yes.
yeah, so, yeah,
Can you write it down over there?
you know what? No, you write
Or
it on that.
oh, okay. I'll write on that. Oh, and share it.
Yeah, I can do that.
Okay.
Don't worry.
Oh yeah. So we'll just keep track of some identities that we will remember, and these should be like some of the top two. Okay. And it's nice to have this visual representation of it because as we get to, especially on the test, they will often show you a block sphere, right? And they'll say, what will a Z operation do to this state? Okay. And you can think about, if you think about it visually, 99% you're going to be right about it, right? So before we do anything, let's say I have the zero state. Everyone knows what direction the vector is pointing?
Here, go ahead.
Up, right? So what happens if I apply a Z gate to the zero state? It's the same, right? You do not have to do any math, and you guys are right. Nothing happens, okay? Sometimes the math will always give you the exact answer, no matter what you do, okay? This is just a representation, and sometimes it can fail at some things, but for the most part, it will get you to the correct place. Okay, so what was it? H x h is equal to Z, and H Z H is equal to X. Okay, those two are the main
Yeah.
facts.
Here, I'm gonna box these and save.
Okay. Yeah, do you want to move on to multi-qubit then?
Yeah.
Okay. Yeah.
You know this gate does 180 degrees on the z-axis?
Yeah. Okay. Hadamard, so far we're not going to talk about it visually because I'll show you guys online what it does. I'll show you a picture towards the end about what it does, but Hadamard we're not going to think about visually because it's more, you know, how the rotation is just like on a plane. Hadamard is like this weird swirl thing, which yeah, it's cross axis. I'm pretty sure it's a diagonal axis actually, but it's a weird rotation.
Yeah, we'll get.
It makes like a cone. That's yeah. Don't think about that visually.
We'll talk about that.
Except for 0 and 1, it'll work out fine. Okay.
Okay. So anyway, now we are going to get into some multi-qubit manipulation. So this is across. We're going to start with two states. So we're going to introduce a new gate called the C0, otherwise known as controlled NOT. And, you know, if you want to represent this as a circuit, then what you can do is this is what this will look like. You'll have like a little dot here, and you'll have a little plus here. So what this is called up here, what this little dot means, is this is called what's known as a control qubit. And what's down here is what's known as the target qubit.
Man, interrupt 1 second.
Sure.
Okay, so first of all, remember that we did not learn quantum first, right? We learned classical computing, most of us, right? And ideas of there being like an if statement, right, is in classical computing, okay? So we're going to approach this gate from that classical mind, okay? Just so that it helps you guys to be introduced to the subject. But we're going to drop that soon, okay? And you guys will see why.
So first we're going to explain in plain simple English and even as like pseudocode program what exactly it does. So say for example we have our control qubit. So this is kind of the qubit that controls the target. So if our control qubit is in the 1 state or is in the 0 state, then don't start. Right? And so, if the control qubit is in 1 state, then what we want to do is change the target qubit from either 0 to 1, from the 0 state to the 1 state, or from the 1 state to the 0 state. And this depends on what state the target qubit is in before we apply the CNOT. So, in plain simple English, this is what the CNOT state does. And the cool thing about quantum is that we can represent this operation as a matrix. So since this is a 2-qubit matrix, or since this is a 2-qubit operation, it's going to be a 4x4. So in its most basic form, this is how we can represent a CNOT gate as a matrix. And this will operate on 2-qubit states at a time. So one question you guys may have is, it's a 4x4 matrix. How do I multiply it? Or how do I apply this to 2 qubits? And so one other thing we are going to talk about today is what's known as the tensor product. So this is how you can represent 2 qubits in a single matrix. And this is important for applications when it comes to this. So say we have a qubit in, say we have 1 qubit called the qubit 0, and this is in the 0. And say you want to tensor this with another qubit that's in the 1 state. So the way this operation works is you can basically do, you can take qubit 0, and you can take each factor. Keep in mind that both of these matrices have to be the same dimension. So this one is 2x1, and the other one is 2x1. Both qubits are 2x1 matrices in this case. So what we will do is we will take qubit 0 and multiply the top part of it by the entire matrix of qubit 1. So, then we take the 0 and do the same thing.
How I remember this is as this is how like matrix multiplication should be, right? It's just like distributing the matrix. It's if you had it horizontally, it would literally be the distributive property. That's all you're doing here.
Yeah. So that's all you're doing here. You're distributing the matrix. And so what this should give you is 0, 1, 1. So this is our 2-qubit state in this case, represented in 1 matrix. Yeah. Oh, my. 0, 1, 0, 0. Thanks for the correction. So yeah, so if we have this 2-qubit state and we want to apply the CNOT gate to this, then what we can do is we want CNOT. And our control qubit in this case is the 0 qubit. And our target qubit is the 1 qubit. So this is the correct notation, right, Sarvesh? It should be 0, 1.
Yes. Control is 0, target is 1.
Yes.
Yeah.
So if we want size this, then when we want to apply this to size, then what we do is we can apply this case to our state. And then from here, you just do basic matrix. So I guess I'll do that real quick. And this should give me Hold on. First entry, 0. Second entry should be 4. So in this case, since our 0 qubit was in 0 state, it did absolutely nothing. So yeah, that's just the basics of how to do CNOT gate in matrix multiplication. Do you have anything?
Yes. How many of you guys know like linear algebra here or have taken linear algebra? Okay, so can I see this real
Sure
quick?
thing.
Okay, so okay, previously, one small thing. What I went over kind of briefly was that we can think of this top cell in this vector right here as the 0 state, and the bottom one is the 1 state. Okay. And I understand that's a bit confusing because if it's a 1 at the top, it's a 0 state, 1 on the bottom, it's a 1 state. But bear in mind, just keep up with me here. In this vector, we can write this as 0, 0, 0, 1, 1, 0, 1, 1. What does this mean? These are the states, okay, like the measured states. If we have a state vector like this, what this means is that out of all the 4 possible permutations of these numbers, if there's a 1 at the top, that means you are in the 0, 0 state. If there's a 1 in the second place, you are in the 0, 1 state, right? Which we see up here. Where we in the 0, 1 state, we have a qubit 0 is 0, qubit 1 is 1. So in the 0, 1 state. And then the bottom 2 are 1, 0, then the 1, 1. Why does this matter? Okay. This, if you guys have taken linear algebra, we can see that this CNOT is what's called a permutation matrix, right? And it's going to essentially flip the bottom 2 rows of our target matrix, in this case, the vector. And if you guys think about it, let's see if we have a 1, 0, right? And we're controlled on this one, it would flip this into a 1, correct? And same thing if we, I'm sorry, I should use this. If there's a 1 and qubit 0, that means we have to flip the first qubit. And if there's a 1 in the 0, qubit 0, we have to flip the first qubit again. So essentially, we're just swapping these 2 rows. Does that make sense? Okay, that's just, I guess, another way to think about it. But yeah. And should I go into the classical?
So wait. I want to do one quick thing.
Oh, yeah.
So if you're gonna have a reverse CNOT, what does that say?
What do you mean?
So okay, I'll just go into
Oh,
So essentially, what we went over just now is if we have a CNOT with the top being the control and the bottom being the target. But what if we have a CNOT, we have another where the top is the target and the bottom is the control. Now this is actually a different. So, and the way to think about this is one identity that we had proven earlier, we can use for this. So this will equal to so what we can do here is that would essentially equal to if we put Hadamard gates, 2 Hadamard gates surrounding it on the 0 qubit and 2 around the 1 qubit. So, oh wait, okay, disregard what I said for now. This is going to be later in the lesson. So yeah, what did you want to continue with survey?
give me 1 second. Okay. Okay, so that was a CNOT gate, and remember how I said this is just because we're starting off classically. Our input states were 0 and 1, right? So classic binary states, and there was a clear target and a clear control. qubit. Everyone is familiar with that, right? Okay. Now we're in quantum. Okay. So now we have to like drop this idea of there being a specific control and a specific target. It works for classical stuff, but if you keep this and if you hold this mentality for some more advanced things, it will get a bit confusing and it won't make sense why. So for now, you can think of as C naught as working fine for classical stuff, but if we're dealing with more like other states, just think of it as an operation, okay? It's just an operation that happens on 2 qubits. We don't have a set controller target, okay? Here's why. If, I'm not gonna do this mathematically just yet, but let's say our qubits were not in the 0 and 1 state, okay? Instead, if we do a Hadamard on the 0 qubit and 1 qubit, okay? That's all we do before. We do a Hadamard on 0 qubit and 1 qubit, and then we apply our C naught, okay? And then at the end, we just do a Hadamard and a Hadamard on 0 and 1. What will that look like, actually? Let me draw that circuit out on Qiskit. Okay. Okay, so let's see what that looks like on Qiskit first. So we'll just make a new quantum circuit. Okay, so we're saying QC is equal to quantum circuit. And let's say we're going to have 2 qubits for this one. Okay, and this time we actually do need 2 qubits. So we're going to first apply a Hadamard gate on the 0 qubit, then Hadamard on the 1. Okay, and then we have to be specific about this, right? QC.CX is how you do controlled X operation or controlled not. So our control, right? Let's say it's 0. Our target is going to be 1. Okay. Then QC dot draw. Well, this is just to represent the idea that the targeting control. I'm not gonna going too in depth in this.
Okay.
This is just to release that idea of targeting control. Okay, so before we look at this is what our regular C naught looks like. Okay, the dot is the control, and the plus is like the not gate, except it has connected to the control. That's the target. Okay, and if we do our state vector, right? We plot this. We get 0, 0, because both are in the 0 state. Our control is 0. Our target was in the 0 state. No flipping is involved, so both are 0, 0. Okay, perfect. Now, if we have our control qubit in the 1 state, okay, what happens? You have your control qubit is in the 1 state because we set it like that. And then we said if the control qubit is a 1, or if it's 1, we flip the target. Okay, does that make sense why it flipped? Okay, so now this is just to like drop that idea of there being a control and target. That is only for classical numbers, because let's say we said we applied a Hadamard gate to the 0th qubit and a Hadamard gate to the 1 qubit. Okay, so far we've gone over what Hadamard gates do, right? And we don't set anything to the 1 state right now. Okay, so this is what it looks like. And then we have to add 2 Hadamard after. Okay, so this is what it looks like. Okay, if we keep that idea of 0 is the control, then qubit 1 is the target. If we apply this, okay, nothing happens, right? Because both were 0. Okay. Now let's see what happens if we set the our target qubit to 1. Okay, which seems weird. What is if we change our target? The target, all that's going to change, right? So let's do that. Set our target to 1. Our target was, remember, setting to 1 is not this number. This is just our target qubit. We're doing an X gate on that. Okay.
Hey, so Grace, real quick,
Huh?
once you're done presenting this, I'm gonna explain
Okay.
how.
Yeah. So it's just offset because this X is like trying to slide in the way. But X is just our initialization. Then we have Hadamard, C naught, Hadamard. Okay. Now if we apply this, what did we do? All we did was set the target to 1. Why did the control flip to 1, right? And if we keep this idea of there being a control and target, it seems like, oh, it's something like changing back in time or something like that. Nothing like that is happening. If you think of C naught as an operator, just an operator between 2 qubits, okay? What this actually does is putting Hadamard, it's called the Hadamard sandwich. You just sandwich you put Hadamards around the C naught actually essentially flips. Okay, the control becomes the target becomes the control. Okay, and if you think of this in terms of, oh, this was the control, this was the target, cause effect, right? It's not going to work out in your head. It's just an operator. Okay, once you get that, then you'll be a bit more free to use this property in some algorithms and stuff. Okay.
Okay, so I'm going to explain how exactly this works on the iPad. So, here, and this is probably the last I will cover today. It is a bit of a tongue blow, but and all right. So to explain what Sarvesh said in terms of the math of it, let me just put some things in context. So first of all, we are going to introduce an operation called the controlled Z gate because that is critical in proving how the target flips to the control and the control flips to the target. So we have this thing called the controlled Z gate. And we will probably go more in depth into what exactly this does later on. But one thing that we need for now to know is that this is a symmetric, what's known as a symmetric operation. All right, so what exactly does a symmetric operation mean? So one thing you might note about the drawing of this is that both of the qubits that this gate is acting on are denoted as control qubits. And so what happens to one happens to the other, what happens to the other happens to the original. So it is known as a symmetric operation. And what exactly this does is if we have a qubit state, so we have a qubit state, alpha 1 of 0, 0. I'm just going to call this psi. I'm calling everything psi. But if we have a qubit state psi of alpha 1, 0, 0, plus alpha of 2, 0, 1, plus alpha of 3, 1, 0, and plus alpha of 4, 1. So pretend we have this state. It's a two-qubit state. It's pretty simple, and each of the alphas denotes the amplitude for each of the probabilities. So pretend we want a CZ, a controlled Z, to act on this. So if we want the controlled Z to be where the C01, so 01 0 is the control qubit and 1 is target qubit, then, you guys know a little information inside here, did you go over that? No? Alright, I'm going to provide some supplemental material on that later, but for now, we're just gonna keep going. So, okay, actually, basically what it means is like the front qubit over here, when you do each of the states, that's qubit 1, and the back is qubit 2. So that's all that is. We just write them in reverse order, not right between the these brackets. Does anyone have any questions about anything? No? All right, cool. So yeah, so basically, if 0 is the control qubit and 1 is the target qubit, then we want to look at two states in particular. So if the control qubit is 0, it does nothing once again. If the control qubit is 1, it does. So two states that we want to look at in this case are this one right here and this one right here. That's a terrible one. Because the control qubit is 1 in both of these cases. If we use the control Z, then, so if we apply control Z to this, the outcome will actually be alpha 1 of 0, 0 plus alpha sub 2 of 0, 1. Nothing happens here because the target qubit is a 0, and that won't change it. And alpha sub 3 is 1, 0, and alpha sub 4 is 3. Okay. But since alpha sub 4, we have a target qubit value of 1, the sign is going to flip at the very end to a negative. So that's if we have CZ of 0. Now, if we have CZ of 0, the states that we will be looking at are the states that we'll want to look at in this case are this one over here and this one over here. Since the control qubit in both of these is 1. Now the target qubit, once again, over here is, the target qubit has a value of 0, so nothing can happen. So the sign goes to the plus, and the last minus.
Aditya, can you, I don't know if we went over this, but can you briefly show what happens when you apply a Z gate mathematically onto the 0 state, and what happens when you put it on a 1 state?
Okay, yeah, sure.
Yeah.
Okay, so just as a little side note, if we apply the Z gate, so that's what, 1, 0, 1. That's a Z gate, right?
Yeah.
That is?
Yeah.
So if we apply that to 0 state, that will give us 1, 0. And if we apply it to 1 state, so it does nothing over there. And if we apply it to 1 state, then it does. So it just flips the sign of the bottom.
Yeah. So one thing is, if you thought about this visually, right? Visually, if you have a qubit in the 1 state, and if you apply a Z rotation on it, it's just rotating about the Z axis. It doesn't do anything that you can see on the Bloch sphere, but outside it adds this phase. Okay, this is just something to keep in mind. That's why the visualization is just a representation. Mathematically is what you're gonna get the whole picture. Okay,
Yeah.
So that's just one important thing to remember. If you're in the 1 state, okay, any Z is what's called a phase gate. Okay, Z will add this negative phase to it. Okay.
Does anyone have any questions about anything at all whatsoever? I know this is a lot, and we're increasing a bunch, so don't be afraid to speak up if you have anything. or tell us if they're cramming too much in one session, what if. But yeah, anyway, so what you guys
Yeah.
wanna know is.
Control the 0, 1.
Yeah.
Which of those alphas are actually affecting the sequence of the boxes? That one.
So for this one down here,
Yes.
oh, for the second one, it's affecting alpha sub 3 and alpha sub 2. Yeah, that's the one we want, those are the ones we. But those are the ones that should be, separate.
And why is on the second one as well, the alpha 2? Yeah. Why is it 1, 0 instead of 0?
Thank you for the correction.
Cool.
And-
we are looking at 4.
Yeah.
For the second thing, because we're referencing 1, 0.
Yeah, same thing for alpha 2 on this one. It's change it from. Yeah.
Yep.
And yeah, that's why the whole what happens when you apply z gate to the one state, that's why this sign flips. Okay. That's why the sign like we saw here, there's a negative phase added, which is why the sign flips, and that's what a z rotation does on the one state. That's why
Yeah,
it's like that.
so,
For the first one, for the-
Yeah.
for the first one,
and what could be 0, 1.
yeah, so essentially, these are the qubits that we're looking at. So in the case of CZ sub 0, 1, alpha sub 2 does not flip at all because the control qubit, although that's 1, the target qubit is in 0. And looking over here, it does nothing to the target qubit if it's already in 0. So the sign doesn't change at all, it stays the same. And the same thing applies to 1, 0. For alpha sub 3, it's in the plus state right now, and so the control qubit is 1 and target qubit is 0. The sign won't change at all. But in both cases, the sign for alpha sub 4 will change.
Yes, and so what you can think about it is all we're doing with the controlled z is if the control qubit, right? We're still in classical, so I'm gonna say control and target. If the control qubit is 0, right? Nothing happens. Okay, we don't do anything. But if the control qubit is a 1, don't think of it as, oh, we flip the sign. No, you do whatever gate is after the control. If we did control X, you would apply an X gate, right? This is control Z, so you apply a Z gate to the whatever state is here,
Yeah.
right? When we apply Z gate to the 0 state, as we saw, nothing happens. But if you apply Z gate to the 1 state, which is why we went in this little tangent right here, it does that sign flip or phase. It adds that phase, okay? That's why the sign flips.
Yeah. And so, because of what you see over here, the outcomes are technically the same, even though alpha sub 2 and alpha sub 3 are being acted on in different cases, even though the sign doesn't change. The outcome for both of them is exactly the same. Only the negative sign applies to alpha sub 4. And so because of that, that's why we call it a symmetric operation. So, long story short, this was a whole spiel on what we call the control Z gate. But if we go back to the example that Starvation in his case, we have control not gate over here, right? And we have catalog gate all over here surrounding it. So technically over here, this right here is an X. I don't know why they do it as plus, but that is an X. And so what we can see right off the bat over here is that we can truncate the bottom to this operation to a controlled Z.
Remember that identity H is equal to Z?
Yeah.
That's what we're using right here.
And I'm going to draw it as, although it's drawn up here as 2 control bits, I'm going to put a Z gate down here just for the sake of clarity. So over here, since it's a symmetric operation, this also is equivalent to target qubit being the 0 qubit now, and the control qubit being the 1 qubit. Now we have Hadamard all over here, and we can apply our identity once again. And what will that give us? Control not gate, except in the other direction. Okay, so that's just a drawing scheme of how it's done. I don't think we have time for doing the math out all the matrices, but I will give you guys the matrix for if we have a qubit in this scenario corresponding to this. So it's again a 4x4 matrix, and it is now 1 0 0 0 0 0 1 1 0 0 1. So that is for this case, for the above.
Nothing. I,
All right, so, I think that's what I have for today. Do you want to demonstrate anything on this kit?
I was just going to say that this concept is something called phase kickback. Correct?
Yeah.
Okay, so you will see this in a lot of algorithms, and this concept will show up multiple times. Okay, basically, we just proved this concept, right? Instead of just blindly believing, you guys saw with, I guess, kind of like algebra, right? You guys are quantum algebra people now. That how we went from the Hadamard sandwich, we saw why, I mean, if you could scroll up a bit, we saw the steps, right? We first used that identity that we learned previous class about H, X, H, how that becomes a Z. And then since Z, or the controlled Z, as he showed with symmetric, you can essentially just flip it. And then we have HZH, which was also part of our identity, and that became an X gate. And there you go. See how it's like flipped? Control is here, target's there, and yeah.
So if you ever see, a control knot where it's like this is a matrix.
Yeah.
And I think that's all we have for today.
Mhm.
So next learning lab is,
Yeah.
You get it now? Oh, yeah, okay.
Yeah, the phase gets kicked back to the control qubit. That's why it's called that.
So that's all we have for you today. Next learning lab for a week, and we will post this as soon as we can. And we apologize that we posted things sooner in the past because of technical difficulties, but we're gonna make sure to post this as soon. All
I'll
right,
stop
thank
the
you.
recording.
Yeah.
Okay.